Hello and welcome to ACSC Academy. This is our NIMSET series and today we'll be covering the part 2 of the chapter Quadratic Equations. In this video we'll be covering the most important concepts of this chapter which will help us to solve any type of question presented to you in the exam, and it will also help you to build a strong foundation for the upcoming chapters in algebra section. So let's get started. In the last video, we had a quadratic equation x squared plus 7x plus 3 equal to 0, and for this equation we had the roots as alpha and beta. So what we had to do was, using these roots, we had to form a new equation whose roots will be alpha plus 1 upon alpha minus 1 and beta plus 1 upon beta minus 1. So hopefully you all might have solved this problem. So let us have a quick look at its solution. From here what we get, alpha plus beta, which is sum of roots of this particular equation, equal to minus 7, and alpha beta, which is the product of roots for this equation, which is 3. Now we have to form another quadratic equation whose roots will be these two. So using these, let us find out the sum and product of the roots for that new equation. So what do we get the sum as? It will be alpha plus 1 upon alpha minus 1 plus of beta plus 1 by beta minus 1. Now here we'll take the LCM, making it same. That will give us alpha plus 1 beta minus 1 plus of alpha minus 1 beta plus 1, and the denominator will become alpha minus 1 beta minus 1. So now let us solve this. It will turn out to be alpha beta minus alpha plus beta minus 1 plus of alpha beta plus alpha minus beta minus 1 upon alpha beta minus beta plus 1. So now using the values of alpha plus beta and alpha beta, we will substitute them here, and after some simplification you will get the sum of roots as 4 by 11. And in the same way you simply have to multiply these two to get the product of the roots, and that will turn out to be minus 3 by 11. So once you get the sum and product of these roots, then in order to form a quadratic equation with these roots, what we'll be doing, we'll simply do x squared minus sum of roots into x. Sum is 4 by 11, so that's substituted over here, plus product of roots, which is minus 3 by 11, that comes from here, equal to 0. So that is our equation. But what we'll be doing here, we can multiply the entire equation by 11, so that converts into this form, and the result turns out to be 11x squared minus 4x minus 3 equal to 0. So that is our answer. Hopefully you might have commented it in the video. And in the same way, there are 3 more examples for using the same equation whose roots are alpha and beta. You have to find out the quadratic equations whose roots will be these 3. So again, you have to solve for these 3 and comment out what are the equations you are getting in our comment section. So now moving on to the next topic, which is the remainder theorem. Now we are already aware about how do we perform the division of two integers. Let us take the simple example. We are trying to divide 10 by 3. Then how do we do that? We take 3 thrice, which is 9, and then we divide it this way, saying that the remainder is 1. And here we are aware about these terms, that this is called as the dividend. Then the one with we are dividing it is a divisor. On the top we have this quotient, and what is left out at the bottom here, it is a remainder. In the same way we perform the division of polynomials as well. If this p of x is a polynomial which is to be divided with another polynomial, that is g of x, then we get the quotient as q of x and remainder as r of x. So we are again aware about the terminology that we can write this dividend equal to the product of divisor and quotient, and to that we add the remainder, or dividend equal to divisor into quotient plus remainder. This is what we have already learned, and that same thing when we apply to the polynomials, then that becomes p of x, which is the polynomial we have as a dividend. that is divided by this g of x. Then as a result of it, we get the quotient as another polynomial q of x, and there is a remainder r of x. So this is what we can write: p of x equal to the product of q of x and g of x, and to that we add this remainder. But from this, what can we say about the degrees of these polynomials? Let us say the degree of this p of x is 4, just for example, and we are dividing it with another polynomial g, which is a quadratic, which means its degree is 2. Then what can we say about the degrees of this q of x and r of x? One thing is for sure, that if you are dividing it with a quadratic, then its result, which means the remainder which will be left out, it will have degree as either 2 or 1 or 0. It can never have a degree which can exceed 2. Just for example, let us take this analogy. If you divide this 3 by 10 in this way, you do 3 twice 6 and you say that the remainder is 4. Is that correct? No. Why? Because this remainder can once again be divided by this 3. It is actually remainder is greater than the divisor. It is not correct. In the same way here, the degree of remainder can never exceed the degree of this g of x, which means your divisor. So you would say the degree of r of x can either be 2 or 1 or 0. And then in the same way, the quotient, if you are dividing a biquadratic with a quadratic, then your quotient may have a degree as 2. So let us actually take out the example and check out if all these facts are correct or not, and what are its applications in the chapter quadratic equations that we'll have a look at. So before that, here at the bottom we have an example. We have a polynomial p of x which is to be divided with another polynomial which is actually a linear equation g of x, and we have to find out the remainder. So let us try to perform it. P of x is given to us as 4x raised to 4 minus 3x cube plus 2x squared minus x plus 1, and it is to be divided with a linear equation that is simply x minus 1. So we are already aware how this division is performed, so let us do it quickly. Here we have 4x raised to 4 and there it is simply x, so we'll divide it with 4x cube. Result is 4x raised to 4. Now you multiply this intermediate quotient with the remaining terms of g of x. So this 4x cube with minus 1 will give minus of 4x cube. Then we perform the subtraction. These will be cancelled out. This will become plus. So 4 minus 3, 1 x cube. Then the remaining terms can be brought down. Plus 2x squared minus x plus 1. You can bring them down one at a time, but it is also allowed if we bring all of them together. Next, there is x cube and x. So we take x squared. So here it is x cube. Then x squared with 1 will give minus x squared. Subtract, cancel out. This will be plus. So 3x squared minus x plus 1. Now next there is x and 3x squared, so we multiply with plus 3x. It will give 3x squared minus 3x. Subtract, cancel out. This will become plus, so 2x plus 1. Now simply with a 2, so we will get 2x minus 2. Cancel out, this will be added. So at the end we get the remainder as 3. So for the given p of x and g of x, we got the remainder as 3 and quotient as this particular polynomial. So let us verify if our intuitions were correct about the degree or not. Here p of x had a degree of 4. It is a biquadratic. G of x has a degree 1. For remainder, it is simply 3, or we can say 3x raised to 0, means it is having a degree of 0. So as we can see, degree of r of x is less than that of g of x. And here we have this q of x, or the quotient, which is having a degree as 3. So again it is holding true. Degree 4 equation when divided with a degree 3 polynomial, then we got quotient having degree 3. So all of these are satisfying the constraints which we have just discussed. Now let us see what are the types of problems do we face that can be solved using this remainder theorem and what all are its applications. Now here we are having another theorem that can be derived using the remainder theorem itself. It says that if p of x is a polynomial which is divided by a linear equation x minus a where a is a constant, then the remainder r of x will be p of a, which means what is p of a? The value, the constant value which you will get after substituting x equal to a in that polynomial. So let us see if it is correct or not. We can verify it using the same example which we just dealt with. This is our p of x and g of x which we had just divided with each other and found out the remainder to be 3. So now let us verify it using this theorem. It is saying that p of x is being divided by x minus a. Here we are dividing with x minus 1, which means a equal to 1. So according to this theorem, the remainder r of x must be p of a or p of 1. So let us find out this p of 1 and check if the given theorem is true or not. What will be our p of 1? We will be substituting 1 in place of x in the given polynomial. So that will be 4 times 1 raised to 4 minus 3 times 1 cube plus 2 times 1 square minus 1 plus 1. So this is simply 4 minus 3 plus 2 minus 1 plus 1. Cancel out. So that gives us 4 minus 3 1 and 1 plus 2 3. And yes, as we can see, the remainder which we had got was also 3. So this was a proof kind of thing using an example which we made for this particular theorem. What is it saying? Let us understand it properly. It is simply saying if p of x is any polynomial that is divided by a linear equation x minus a, then the remainder has to be p of a. And it makes sense actually, because if it was a root, if x minus a was the root of this polynomial, then you would have got the remainder as 0 for sure. But if you divide it with some another polynomial x minus a, then its remainder has to be p of a, which means it is kind of a diversion thing from, this is the root and from that you are diverting to a, then remainder will shift these many places ahead. So it has to be given by p of a. So this theorem can help us solve some simpler problems and we will not actually need to divide that whole thing. As you can see, that entire division of polynomial procedures is not required here. We can simply find out the value of p of a and we can declare it to be the remainder. So next time, whenever you encounter such questions where you have been given a polynomial p of x and it is being divided by a linear equation and they're asking you to find out the remainder, then there is no need to divide it completely. You can simply substitute this particular value in that polynomial, for example p of 1 in this case, and you can declare that to be the answer. That would be the remainder of that division. So this is a trick kind of thing which you can use for solving the problems. Now moving ahead with the same remainder theorem, we will be exploring if there is any other method of finding out the remainder without actually dividing the two polynomials. So here we are considering p of x to be the same polynomial which we had till now, but now it is to be divided with this another polynomial g of x, which is actually a quadratic equation now. It is x squared minus 1. So we have to divide p of x with g of x and find out what is the remainder. So for this particular problem, you are already aware about one method, that is the division of polynomials. And for division, you can also have another way of, say, synthetic division. But the problem is that in either of the two cases, you actually need to divide the two polynomials together and then you need to find out the remainder. But we are trying to explore a method in which no division is required. Without actually dividing the two polynomials, we have to estimate what would be the remainder of the two after their division. So here we will be taking help of the remainder theorem. And what does it say? As we already saw in the previous videos, that we can write p of x as g of x into q of x plus r of x, where your q of x is quotient polynomial, r of x is the remainder polynomial, and these p and g are already given to you as dividend and divisor respectively. So from remainder theorem, we saw that the degree of the remainder polynomial is always less than the degree of the divisor, or you can say g. There we had taken the example that if degree of g is 2, then the remainder can have a degree as either 0 or 1 or 2. But it turns out that, as we saw using an example, that the equality is not allowed. There is a strict inequality, which means the degree of remainder has to be strictly less than the degree of the divisor. So from this we reach up to the second method, which says that, as in this case our g of x is a quadratic equation, which is x squared minus 1. So using this we can say that if g of x is a quadratic, then the remainder which will be resulting out of the division of p of x and g of x, that can have degree either as 0 or as 1, which means it will be either a constant or it will be a linear polynomial. True? So we can say that, let us assume that the resulting remainder will be ax plus b. Now here these a and b, they are the simple constants. So we are not actually dividing the two, we are assuming that the resulting remainder can have the form of ax plus b. Why so? Because it can have degree as either 0 or 1. So we are taking this highest possible degree of the remainder and we are making a general polynomial of that degree. For example, if your g of x would have the degree of 4, then you would say that the remainder can have the maximum possible degree as 3. Then in that case you would have assumed r of x as something like ax cubed plus bx squared plus cx plus d. This is what a general polynomial we are forming out and assuming that to be the remainder. Now, what is the use of doing so? Let us see. Now from here what we'll be doing is, we will be writing over here, we are having, so now what are we going to do is, we will write this p of x equal to some q of x, we do not know what is that quotient because we are not dividing them, into g of x. Now here we are aware about the g of x and we can write that as a factor of 2, which is x minus 1 and x plus 1. So we can write g of x as a factor of these two and plus the remainder. But here instead of remainder we will be writing the polynomial which we have assumed, and that is ax plus b. So now what are we going to do is, our goal is to eliminate this entire term because we do not know what q of x is. We know p of x, it is already given, and we already know the remainder, yes, in terms of a and b, but we are aware about what is the remainder, but we do not know anything about this quotient term. So we are trying to eliminate that. And how we will be doing that? Let us see. If you substitute the value of x equal to 1, then what we will get? P of 1 equal to, now here as you can see, why did we take 1 only? Because that 1 is a factor of this thing. So if we substitute x equal to 1, then this will become 0 and this entire term will be gone. So we will get p of 1 equal to, simply from this side, a into 1 plus b, which is a plus b. Similarly, when we substitute x equal to -1, then we will get p of -1 equal to, here again -1 is the factor of this particular term, so that will become 0, nullifying this entire term. So we will get p of -1 as a times of -1 plus b, which is -a plus b. So what was the use of doing this thing? Now let us see. We did this because this 1 and -1, they were the factors of this g of x, and as a result of that we got p of 1 and p of -1 in the form of, or in the terms of, these a and b. Now what we'll be doing is, we already know what the value of this p of 1 is from this particular polynomial. We will say p of 1 is 4 minus 3 plus 2 minus 1 plus 1, and which turns out to be 3. Similarly, we will find out p of -1. It will turn out to be 4 plus 3 plus 2 plus 1 plus 1, and this is 11. So we will say that p of 1 equal to 11, and we just found out p of 1 as a plus b. So a plus b equal to, p of 1 is 3, hence a plus b is also equal to 3. Similarly, p of -1 is 11, so minus a plus b is also 11. So now as you can see, here we have got two equations in two variables. So they are the simultaneous equations. So we will simply add them and we will find out what are the values of a and b are. So after adding, we get 2b equal to 14. So b equal to 7, and you substitute the value of b over here. So you will get a plus 7 equal to 3, a equal to -4. So now what are we going to do is, we have got the values of a and b. So now we will be substituting them back to the remainder equation that we had assumed. What had we assumed? We said that r of x is ax plus b. So we'll substitute a equal to -4 and b equal to 7 over there. So now we have got the remainder, and as you can see, it is the same that has been written over here, which was our expected answer. So using this method as well, we got the same remainder. You can also verify using the original division method that you get the same remainder or not, but here also we have got the same result, and this method was actually shorter and easier than actually dividing the two. In case the polynomials grow too large or the degree increases, then it becomes difficult to divide them accurately. It is time consuming and also error prone. So this is the second method that we can go for using remainder theorem. And in this method, what do we actually do? We make assumption about the remainder. And how do we make that assumption? Using the degree of g. If degree of g is, let us say, p, then you will assume r of x to be a general polynomial of the degree p minus 1. Why p minus 1? Because degree of remainder is strictly less than the degree of the divisor polynomial. So what you will be doing is, if your g is having a degree of p, then you will assume r to be a general polynomial of degree p minus 1, and then you will be writing it in this particular way, as a result of which you will get simultaneous equation. Here we got two equation in two variable. If your p increases, if your p becomes 4, then you will assume r to be a general polynomial of the third degree, which means a cubic equation. Then in that case, you will get three equations in three variables. That will be a little tedious to solve. Similarly, if p increases even further, then you might get 4 equation, 4 variable, or even more than that. That is definitely not practical to solve, and such big problems will not be given in the exam. So restricting it just to quadratic itself, this is one way of finding the remainder without actually dividing them. So one thing you have to keep in mind that we will assume R to be a general polynomial of this form ax plus b, and then we will solve it in this particular way. We will substitute those values which will make this term to get vanished, and as a result of it we will be able to get the p of, let us say, alpha and beta are the roots. These are alpha and beta, the roots of this g of x. For this we will have to first solve this g of x equal to 0 and find out what its roots are. Let us say alpha and beta. So then you will be substituting them and you will be getting p of alpha equal to something, p of beta equal to something. Then you will reach to these simultaneous equations. Then you will solve them, and as a result you will get the values of these a and b, which you will substitute back over here in the assumed equation, and as a result of that you will reach here, you will get the actual remainder for this division. So this is how you can find out the remainder of this division of two polynomials, and there are a lot of problems based on this theorem as well, so we need to practice it thoroughly. We will be watching some more examples from this topic in order to gain confidence in this.